start with 7. Okay. So anyway, this is a simple pendulum problem, and you'll be given the formula for the period of a simple pendulum on the exam. That's just 2 pi times radical L over G. And so if we draw the initial and final conditions here, okay, here's the initial condition. Actually, I guess it would be more appropriate to draw this in black. Okay, so here's the initial condition. And here is the final condition. Okay, so is the time that it takes to go from here to here equal to a full period? Okay, what fraction of a period is it? Okay, yeah, it's 1/4. So after we've calculated the period, we're going to have to divide by 4. So we'll say that delta t is equal to t over 4, which is going to be equal to pi over 2 times radical L over G. We know what everything is except for L. So how do we find what L is? The length of the pendulum? Well, the string, or the rope, can be thought of as the hypotenuse of a right triangle. And what's this leg of the right triangle? Yeah, 150. And what about the horizontal leg? Yeah, that's 75. So how do we use this to calculate the length? Yeah, Pythagorean theorem. Okay. So this is going to be the square root of 75 meters squared plus 150 meters squared, all to the 1/2 power. And 75 squared plus 150 squared. Okay, that is 168 meters. And now, we just plug that into our formula for 1/4 of a period. That should give us 6.5 seconds. Let me make sure that it does. Yep, it comes out. Okay. So,
So the 16 divided by 4, how did that come into pi over 2? And the rest of that?
Well, when we take 2 pi and we divide it by 4, it cancels out the factor of 2 and leaves 2 in the denominator. Does that make sense? Okay. So any other questions about this one? So we've already done problem 8. So 7 is the only problem we didn't do. That's surprising. Then let's move on to the practice problems. And I'm going to start with conceptuals, just like I did in the lecture review. So here we have a position time graph, and we want to calculate the maximum speed of the oscillator. So based on the information that we can glean from this graph, what would be the most useful formula to use for the maximum speed? Yeah, Vmax is equal to what? Well, what quantities can we get from the graph? We can get frequency. Well, we can get it eventually. We could get period more directly, right? So period and amplitude. And so what is the amplitude? Yeah, 2 meters. And what is the period? I mean, like to the nearest second. Yeah, this is just past 1, and this is just past 8. So the period is going to be 7 seconds. Now, does anybody remember a formula for Vmax in terms of amplitude and period?
Two pi FA.
Okay, yeah, 2 pi A over T. So now we just plug in our 2 meters and our 7 seconds. That should give us 1.8. 4 times pi is about 12. Yeah, that makes sense. All right. Yeah, you could have, gotten the frequency from 1 over 7 seconds and then used the formula 2 pi FA instead. Astrid, did you have a question? Oh, okay. Yeah, the amplitude is the maximum displacement from equilibrium. So that is this distance right here. No problem? Any other questions? All right. Here we have 2 blocks oscillating. 1.5 the frequency of the other. We want to know how many times more massive it is. And so this is a ratio reasoning problem. I guess the sort of gives that away. But anyway, ratio reasoning. So the first thing that we have to do in ratio reasoning is find the relevant formula. And what would be a useful formula for this case?
Two pi f over square root of K over M.
2 pi f, what?
Is equal to square root of K over M.
Okay. Right. Okay, this includes the frequency, it includes the mass, and so the next thing that we need to do is solve for the quantity we need to change in. And so we're trying to find the factor by which what quantity changes. Right. Mass. So maybe I should break this down into steps. First thing we want to do is square both sides. Yes, this is the equation for the frequency. A simple harmonic oscillator, or mass on a spring specifically. If we square both sides, we end up with 4 pi squared f squared is equal to k over m. And now, well, let's flip both sides over so we can get m in the numerator. So we're going to invert both sides. That will give us 1 over 4 pi squared f squared is equal to m over k. And then finally, we can solve this for m by simply multiplying both sides by k. This gives m is equal to k divided by 4 pi squared f squared. All right. So now, we need to set up our table of quantities and value, or quantities and factors. There are 4 quantities on the right-hand side. They are K, 4, pi, and F. So as we go from oscillator A to oscillator B, by what factor does the spring constant change? Okay, yeah, these are identical springs. Identical means they have the same spring constant. So K changes by a factor of 1. What about the number 4? Yeah.
5/8.
Huh?
Nothing.
4 is always the number 4. What about pi? Yeah, pi is always pi. And what about F?
1/2.
Yeah, 1/2. All right, so now we're going to rewrite the right side, replacing quantities with their corresponding factors. So we replace the k with a 1, we replace the 4 with a 1, we replace the pi with a 1, and we replace the f with 1/2. And so what do we get? Oh, I guess I gave you the answer. So, yeah, it's going to be a factor of 4 times more massive. All right. Let's see. Okay. Let's take a look at this one. It's a little bit different than the previous one. Oh, you know what? I forgot to write an essay. See how it says write an essay in complete sentences? Unfortunately, I didn't give myself much room. But I showed you what kind of an essay I was looking for in the lecture, so maybe I'll just let that one example be enough. If you want to see me. Okay, so in that question, we simply asked by what factor a particular quantity changed. In this problem, we're not just asked for the factor by which a quantity changes, but for the new value of the quantity. Okay, so now the springs are different, and the masses are different, but the periods are equal. And so given the spring constant of A, we want to find the spring constant of B. So we've already seen the formula for frequency. So the formula for period is just the inverse of that. Okay.
Gotta do stuff for
Period is going to be 2 pi times radical m over g. And
You got this.
so what do we need to solve this for?
Yeah, I gotta go do research for seminar.
Wait a minute. Something is amiss. Yeah, that should actually be m over k, not g. Huh? Yeah, what do we need to solve this thing for? Yeah, the spring constant. So, I won't go through all the steps this time. The spring constant is just going to be equal to 4 pi squared times m divided by t squared. All right. So now we can go straight to setting up the table of quantities and factors. There are, once again, 4 quantities on the right-hand side. And by what factor does the number 4 change? Right. And pi? Right. And m? Yeah, m sub b is twice m sub a, so finally, what about t? Yeah, that's also 1. So now we rewrite the right-hand side. Notice I'm not writing an equals sign. I'm not going to write an equals sign in front of this because k is not equal to what I'm about to calculate. What I'm about to calculate is not k, but the factor by which k changes as we go from oscillator A to oscillator B. So I replace the number 4. Well, I don't know how I did it, but I apparently crashed the program. I may have accidentally pushed the button on this pen. But I guess it would be a good time to return to graded quizzes. All right. What was that? Oh, you know, I didn't think about the test, but I can run back to my lab and my office and get those too. This might take several minutes. Okay.
He's like, well, then I wasn't worried you could see it that far away. I was like, I was thinking of the recording. Yeah.
That gave us 4 pi squared times m over t squared. We came up with our table of quantities and factors.
We did actually. We did them all in one. We just did them on a separate one. What's the
And we have 4, pi, m, and t. So by what factor does 4 change? Okay, right. 1 pi and m.
like pi?
Okay, right. And t, 1. Okay, so we rewrite this as 1 times 1 squared times 2 divided by 1 squared, and that'll just give us 2. All right, so the spring constant is directly proportional to the mass, and 2 is not our answer though. Okay, we're not asked to find the factor by which the spring constant of B is larger than spring constant A. We're asked to find the actual spring constant of B. So we can say that K sub B is equal to 2 times K sub A, which is just going to be our 100 newtons per meter. All right. Okay. I guess we've done every kind of ratio reasoning problem there is. Boy, I've put a lot of ratio reasoning problems. Okay. So let's see, here we have a hanging block that passes through equilibrium at 2 meters per second and returns to equilibrium 0.75 seconds later. We want to calculate the total distance that it traveled. All right, so let's see. Does anybody have a suggestion about what formula we should start out with here? Well, it says something about returning to equilibrium after a certain amount of time. So it seems like the period might be a useful thing to, well, it might be something that we can get from the information in the problem we use to find something else. So let's start with the formula for the period. Okay.
Switched over to non-overhead.
We're missing something.
You know what I mean?
I know we did, but I don't know how to do that here.
How do I find it?
I have to switch. This is the same thing, and it would be a different page here, but there's no other page.
No, I have like 5 through, what's it, 11?
It would be here. In one of these.
Total distance and travel. We need we need is the amplitude, okay?
Sorry, something's wrong with the section.
Ultimately. And we can, okay, yeah, I'm back now. This has been one of the worst weeks I've had in terms of sleep deprivation this entire academic year. So don't judge me. You have no right. Okay. So anyway, this speed, 2 meters per second, what variable represents that quantity? the speed at which you pass through equilibrium. What is that? Yeah, Vmax, right, okay. So Vmax is equal to 2 pi over t times the amplitude. Now, how can we find t from the information given in the problem? If it passes through equilibrium, let's say it's going back and forth like this, all right? It passes through the halfway point, gets to one extremum, and then comes back to equilibrium. What fraction of a total period is that? Okay, right, that's 1/2 of a total period. So the period is simply twice that time interval that's given. Which is 2 times 0.75, which is just 1.5, which is per second. Okay, 1.5 seconds. So we know the period, and we need to find the amplitude. All right, so we solve this for amplitude. That's going to give us Vmax times t divided by 2 pi. All right, and Vmax is our 2 meters per second. Our period is 1.5 seconds. And so basically this is just 1.5 divided by pi.
Do you have the original files?
Which gives 0.477 meters. All right. So is this the quantity that it's asking for, the total distance between those two, or the total distance traveled between those 2 points in the motion? Here's equilibrium. Okay. Here's the top of the motion, here's the bottom of the motion. Basically, it starts here, it starts at equilibrium, it goes this way, goes to one extremum, turns around, and comes all the way back to equilibrium. And we want to know what total distance that is. What total distance was traveled. So, how is that related? How is that distance related to the amplitude? Half of the amplitude?
2 times the amplitude.
Okay. Yeah, well this right here is the amplitude, right? So if I travel from here to here and then back, I've actually traveled through twice the amplitude. So we know that the distance, let's just go ahead and write it out. The distance is equal to 1/2, or twice the amplitude rather, 2 times A. That should give us our 0.954. And certainly looks like it does. Okay. So I think I better save this. Before I move on. Let's hope that the computer doesn't crash again. All right. Here's a nice one. We want to find the position, speed, and acceleration at a particular clock reading. And so we're going to need the formulas for x, v, and a in terms of t.
I have this one there, Don.
So x of t is just equal to a times the cosine
250.
of, well, in this case, we're given the frequency. So we'll express the angular frequency in terms of frequency. This is just 2 pi f times t. And so now we just have to start plugging in numbers for the position function. What is the amplitude?
0.076 meters.
Okay, right, 0.076 meters. If it's released there, if it's released from rest at that position, it's never going to get further away from equilibrium than that. Now, frequency is given as 2 hertz. The clock reading is given as 1.6 seconds. And so that should give us 0.0235 meters. It doesn't explicitly state in this problem, but we always assume that equilibrium is x equals 0, or actually y equals 0. So, assuming y equals 0 at equilibrium. So this is telling us that its position is about 2 1/3 centimeters above its equilibrium position at t equals 1.6 seconds. Now, the velocity function in terms of frequency is going to be negative 2 pi f a times the sine of 2 pi f t. And that should be little t, not big T. Okay, well, plugging in the same numbers for A and F that we did before, that should give us our negative 0.908 meters per second. And the acceleration is going to be negative 4 pi squared f squared times A times the cosine of 2 pi f times t. And that should turn out to be negative 3.70 meters per second. And of course we have to put boxes around all these. But the most important thing is to make sure your calculator is in radians mode. No, it won't. You probably should just switch your calculator radians mode for the entire exam. Just make sure you remember to put it back into degrees mode after the exam is over. But pretty soon we're going to get into material where it's a lot more useful to know the angle in degrees. I really need to check these answers. I believe in myself. Okay. Okay. That's very similar to the one we just did. Here's one that's a little different. We are given the displacement as a function, or displacement from equilibrium, as a function of time and position on a string, and the general form of the displacement equation is the amplitude times the cosine of omega t plus or minus, wait a minute, the omega t second. Yeah, I keep forgetting this. I want to do the college physics version of this, which is 2 pi over lambda times x. That's a lambda, okay? Minus 2 pi over capital T times little t. Okay, this is a pi. There you go. So we're given the wave speed and we want to find its frequency. So does anybody remember the relationship between the speed of a wave on a string and, or any wave really, and the frequency of the wave? I'll give you a hint. The speed is v, and the frequency is f. Does that help? Well, v is equal to f times, lambda. The fundamental relation for waves. So we can find the frequency from the speed if we have the wavelength. So how do we find the wavelength from the displacement function that we're given? Okay. Right. We know that the coefficient of the x is 2 pi over lambda, and the coefficient of the x in this particular displacement function is 0.5 times pi inverse meters. We're going to leave off the units, but we have 0.5 times pi is equal to 2 pi over lambda. And then lambda is simply going to be 2 over 0.5, since the pi's cancel out. And 2 divided by 1/2 is 4. And so now, well, let's put on the units now. And now that we have the wavelength, we can just plug that into our formula for the frequency. Frequency is equal to the wave speed, 8 meters per second, divided by the 4 meters for the wavelength, which is simply 2 hertz. Well, I don't feel comfortable just writing 1/6, but I'm not sure. We'll take it 2.00 hertz. All right. I think I need to change this probably to make it more confusing.
Are you gonna have all the equations right, like V is S football?
Yeah. Yeah. Okay. So, wow, it's already starting to take a long time to save this. Voicemail. Okay, so that's a similar problem. That's a similar problem. That's a similar problem. That's a similar problem. Because, well, actually, this one's a little bit different. A little bit. Not much, but a little. Okay? We're given another displacement function, except this time we have the coefficients of both x and t. We're told the tension of the string, and we want to find this linear mass density.
Oh, you found it?
So, what's the relationship
Yeah, that's it.
between tension and linear mass density? Or, I'm not really sure that's what I meant. But when you think of tension and linear mass density, what else do you think of? This is is what Freud referred to as free association. I'm all right, seriously. Don't call 911 or anything. Oh, yeah, you wouldn't mind, would you? Okay, I'll give you a hint. What I think of is V is equal to the tension of the string divided by the linear mass. All right. So, we're trying to find the linear mass density. So we solve for that. And we end up with T sub s divided by V squared. Now we know what the tension is, but we don't know what the wave speed is. So how can we find the wave speed? What was that? Oh, actually, Vmax is something different. It's very important that you not get V confused with Vmax, okay? Because V is the speed at which the waveform travels from one side of the string to the other side of the string. Vmax is the maximum speed of a point on the string that's wiggling up and down, all right? So there are two speeds that you need to keep very separate in your mind. Okay, the speed of a particular point on the string is always changing and has its maximum value as it passes through equilibrium. That's Vmax. V, all by itself with no subscript, is the speed at which the waveform passes from one end of the string to the other. So this particular problem does not relate to Vmax, the speed of a particular point on the string. It only relates to the speed of the waveform along the string. And so, what's the formula for the wave speed along the string? I mean, the only one other than the one I just gave you. Oh, lambda over period, right, okay. So, we could also make it lambda times, or frequency times lambda. Either one is fine. We just have to be careful not to get T confused with T sub s.
Oh, both of those.
T with no subscript represents the period, and T with the S subscript represents the tension of the string. Okay. So, how are we going to find the lambda? Well, I guess we already did this once, didn't we? Does anybody remember how we did it all those minutes ago? Okay, right, the coefficient of the x is always equal to 2 pi over lambda. So 2 pi over lambda is 3 pi, and that means that lambda is going to be equal to 2/3, because the pi's cancel each other. And let's go ahead and write this as a decimal, in decimal form. So this is 0.67 meters. Now, how do we find the period capital T? If I write down the general form of the displacement equation again.
Yeah.
Okay, so how are we gonna get big T out of there?
So you go to 400 pi.
Oh, 400 pi is equal to what? Right, 400 pi is 2 pi over t. And so solving that for t, we get 2 over 400. And, you know, I should be able to convert that to decimal point in my head. 1 over 200, that's 0.005. Wow, that is a short period. Okay. And so now that we have lambda, we have t, we can go ahead and bring this down. Bring it down like this.